Okay, let's look at practice quiz number 2 for Algebra 1, learning target number 1, exploring functions. So we're going to start at standard 1.1, label each of the 12 representations as linear, exponential, or quadratic. So personally, from what I've seen from our students, we really like to start with the graph. So we're going to start here with linear. What word do you see hidden inside linear? I see this word, line. What do you see right here? I see a straight line. So I'm going to mark this one as linear. All right. Now, we've got these two. One of them is quadratic. One is exponential. Turns out quadratics, when you graph them, have a U shape like that. That makes it a quadratic. That U right there. So that is going to be quadratic. All right. I'll try to write that with another pen so it's a little bit clearer there. That is quadratic. All right, then that makes this last one exponential. What's the key with an exponential? You can see it goes up really fast. It curves up very quickly. All right, so we're going to use these colors to keep track of stuff. All right, next one. We can take a look at the tables right here. So how are they growing? Well, if I look at this first table, how is it growing from 5 to 7, 7 to 9, 9 to 11? Now, when I say it, I mean the number of tiles. How is the number of tiles? It's going up by 2. Be more specific. Up means what? Plus 2, plus 2, plus 2. Do we see how it's adding every time? It's adding 2 tiles, adding 2 tiles, adding 2 tiles. When it adds, adding or subtracting growth, that is linear. Okay? Let's look at, maybe let's go to this one on the right over here. Now on this one, I can see the number of tiles goes from 3 to 15, 15 to 75, 75 to 375. What's the pattern there? It's multiplying by 5, multiplying by 5, multiplying by 5. In that case, if the number of tiles is growing by multiplying, that is exponential. It is multiplying every time. So we're going to call this one exponential. Okay. Oops, I should have used orange. And the last one, that makes the last one quadratic. Okay. That makes the last one quadratic. All right. Let's go down to our equations, our rules. Now, this first one, x plus 2 squared minus 1. The key there, what do we see? Is this right here. That little 2, that's an exponent to the second power. We read that as squared. All right? Square. We read that as squared. Anything squared, the key word for a quadratic is squared. This one is quadratic. It has an x squared. All right. Let's make moves over to this one on the right. Now in this one, I see it written as 3 times 5 to the x power. The key here is that the x, the figure number, the input, is the exponent. All right. This up here is an exponent. What this means is, it means 3 times 5 times 5 times 5, x number of times. Okay, we just keep multiplying 5 by itself. That is exponential. Meaning, this last one in the middle is linear. Notice on linear, no exponents, no squared exponent, no x exponent, nothing. All right. Let's look last at the patterns to start with up here. Now, how is this one growing? Well, from here to here, I see it added those 2 squares. Then on this one, I see it added those 2 squares. Those are the new squares every time. How many squares are we adding? Well, looks like we're going plus 2. If it's adding, that means it is linear. All right, let's look at this middle one. What shape do we see here? I see this 1 by 1 square in the middle, a 2 by 2 square in the middle, a 3 by 3 square in the middle. If you see that square right there, that changing square, That's your key, that it is quadratic. This last one then must be exponential. How do we know? Well, let's see what we've got here. I see a group of 3 dots. Then I see 15. So instead of one group of 3, there's 5 groups of 3. And then here I see 5 groups of 15. So this quintuples. It multiplies by 5 every time. All right, so that is standard 1.1, matching quadratic, linear, and exponential. Let's go down to golden standard 1.2. Now here, the key is to remember that x you could think of as the figure number, and x is always left and right. Y, think of as the number of tiles. Y is up and down, okay? So the way we think about this is we have our y-axis, which is the up and down space, and our x-axis, left and right. So to plot A to start, my first number is always my x. Think about the alphabet. Our points are always written as x, comma, y. X, y, z. X comes before y. So I'm going to go 4 on the x, and then -2 on the y. So where is that? -4 on the x. I'm sorry, just looking for a pen. 4 on the x. 1, 2, 3, 4 on the green. Down 2 on the y. I'm going to put a dot right there and label it A. For C, C says 0 on the x. That means if I start in the middle, I don't go anywhere. But I need to go up 5 on the y. Start at 0 on the x, go up 1, 2, 3, 4, and 5, and there is C. All right, so let's figure out B here. For B, starting at 0, how far do I go on the x first? -1, -2, -3. So B, I start at -3. All right, I can write it in green to be more consistent. And then, where is my y? I'm going to go up 1. So -3 on the x, up 1 on the y. For D, I'm going to go, starting at 0, 1, 2, 3 on the x, green on the x. And then the y, do I go up or down? No, I don't go anywhere. So I'm 0 on the y. All right. Next step, plot the next 2 points for this tile pattern. Think of it like a tile pattern. How is it changing? So I could think of this point as 0 on the x. 0, figure number 0 has 12 tiles. 10, 11, 12. Figure 1 has 10. 1, 10. I know that's 1 because it's halfway between 0 and 2. This one, figure 2, has 5, 6, 7, 8. What's the pattern? 12, 10, 8. Well, in that case, the y value, the number of tiles, is going down 2. So as I go to figure 3, I'm going to go down 2 tiles at figure 3. Down 2 tiles to figure 4. So what are the next 2 coordinates? This is the point. Figure 3 has 6 tiles. 6 tiles right across here. Down 2. This next one, figure 4, has 4 tiles. So my next 2 points are 3, 6 and 4, 4. All right, that's the front side. Let's move on to the back. All right, so on the back, first one, let's talk about domain and range. Domain and range. So a boy walks along a straight road from his home to a bus stop. Now, the first question says, between which hours, which should say seconds. Oops, that should say seconds right there. That's a typo. We'll make sure that's fixed. Between which seconds is the boy walking back to his house? This should also say seconds here. That will be fixed. Now, if we're talking about seconds, that means we're talking about x values because you can see it says time in seconds. All right? Seconds. Well, here, 0. If he's 0 meters from home, that means he's at home. So as the distance from home goes up, he's walking away from his house. So then the part he's walking back to his house must be this part. The distance from home is going down. He's walking back to his house. So what times are those? Well, it looks like it starts at 50 seconds and it goes to 70 seconds. All right. Now the next question says, if you want to know where that is, I'll highlight our answer here. How far away is the bus stop? Well, the bus stop is where he stops. It's where he waits. So how far away is that bus stop? That means we're going to be looking at the y-axis. How far away? That's distance. The bus stop is going to be located where? The bus stop is going to be located where he stopped. All right. So where is the bus stop? Looks like it's at 160 meters. Okay, 160 meters. It's where he stopped. You get to the bus stop, you wait there. All right, identify the domain and range of the graph using inequality or interval notation. You can use either here. I will show you both. Remember, domain. Domain means x, your x values, okay? So domain is your x values. It is left to right, okay? So how far does this graph go? Left and right. Well, I see an arrow on this side, so that means it goes forever to the left, which forever to the left is what we call negative infinity, not included. And I see an arrow on the right, which means it goes forever to the right, so to positive infinity. So we could write our example like this, negative infinity to positive infinity, or we could do that symbol, which means all real numbers. All real numbers. Our range, on the other hand, our range are y values. Okay? Our range is y values. Domain is x, range is y. Our y values starting from the bottom to the top. Now, if you think about range, how far down do we go here? Well, there's an arrow. So I'm going to go forever down. So I'm going to start at negative infinity. Now, as I go up, I see that we stop right here. We stop at this value. What is that value on the y-axis? It's 3, between 2 and 4. So this graph starts at the bottom, goes up, and then hits 3, inclusive. It includes 3. Right? It goes through the y value of 3. You can write it like that, or like this. Y is greater than negative infinity and less than or equal to 3. Notice, or equal to gets a bracket, greater than just gets a parenthesis. All right, that is domain and range. Let's do the last section, Golden Standard 1.4. Evaluate when x equals 5. All right, so I'll start with the top one. Solve for y when x equals 5. So how many tiles are in figure number 5? We're going to take this x right here, and on figure 5, we're going to take this value and substitute it in. So what does that look like? That's going to look like y equals 1 times 3 to the 5th power. Now remember your PEMDAS, order of operations. Exponents come first. What is 3 to the 5th power? 3 to the 5th power, because this is exponential, that x is an exponent, that's 3 to the 5th is the same as 3 times 3 times 3 times 3 times 3. There are 5 3's being multiplied together. So 1 times 3 to the 5th power is 343. So it equals 343. That is the solution. Okay? Figure 5 has 343 tiles. Let's try the next one. When we look at this figure, it turns out, what can we see here? Well, I see a square, a row in a row with 2 dots. There's my 2 dots. I see a bigger square, a row in a row. That changing square makes me suspicious it's quadratic. So when x equals 5, I'm going to take that x and substitute it in for everywhere I see an x. So what does that look like? Y equals 2 plus. I'm going to take that x, put it in for 5, and 5 plus 2. Now, first step when you solve this, plus. Parentheses come first. Do this group first. 5 plus 2 is 7. What comes first, 2 plus 5 or 5 times 7? PEMDAS, P, parentheses, exponents, no exponents. M, multiplication. 2 plus 5 times 7 is 35. 2 plus 35 is 37. All right, let's look at this one in the bottom left. Solve for y when x equals 5. This is that same pattern from the front. I can see that in this one, what changed? It added these 2 tiles. It is linear. So I'm going to take this x equals 5, and I'm going to substitute that 5 in right there. So the number of tiles is 5 plus 2, 5. Now, be careful here. 2x does not mean we write 25. What is the 2 doing to the x? When there's no symbol between it, it means they are multiplying. Just like up here, what are the 5 and 7 doing? They are multiplying. That's where 35 comes from, 5 times 7. Just because there's no symbol, that means multiply. So what should we do first here? Y equals 5 plus 2 times 5. Multiplication comes before addition. So we multiply first. 2 times 5 is 10. 5 plus 10 is 15. So figure 5 has 15 tiles. All right, and the last one. I'm seeing this x squared right here, making me think it is a quadratic. So we're going to take this x equals 5 and substitute it where we see those x's. Okay? So y equals 2 times, what's going to replace that x is a 5, because we're looking for figure 5, plus 5 plus 1 squared. All right. So 5 plus 1 is 6. Do what's in the parentheses first. 5 plus 1 is 6 squared. Next, exponents. I do see an exponent right there, a power of 2, which means squared. So I'm going to leave this one the same. 6 squared is 36. Multiplication, I see it right there. 2 times 6, again, when they're just right next to each other with parentheses, it means multiply. So 2 times 6 is 12, and 12 plus 36 is 48. All right, my friends, I hope that's helpful. Good luck on your quiz.